Hello, everyone, and welcome to tonight's Astronomy on Tap edition, the last of this wonderful year of 2020. My name is Laurent, and I will co-host tonight's edition with Jake, who is in charge of the pub quiz. So tonight I will start by presenting some space-related news, and following that we will have our first talk by Dennis Bodewits, during which you can ask questions on all our social media, Facebook, Twitter, YouTube, and I will ask these questions at the end of the talk. Following that, Yamila Miguel, our second speaker, will present her topic, and then a round of Q&A. After a quick break, Jake will host the pub quiz on Zoom, and you will have a chance to win an amazing prize, so don't miss it. And finally, we will share a beer in our Zoom pub, during which you can brag about your victory at the pub quiz and directly talk with the speakers if you have questions or if you just want to enjoy a nice beer. So as the first news, exactly 48 years ago, on the 7th of December 1972, Apollo 17, on its way to the moon, looked back and took an amazing picture of the Earth called the Blue Marble. So don't hesitate to go check it out. It's really cool. Yesterday, SpaceX has launched its 100th successful Falcon 9 launch, making this year the busiest of the company with 23 launches. What's really interesting is that most of the part of the rocket have actually been reused, including the first stage booster, which has been launched and landed a grand total of 7 times. So it's really good for reusability. Yesterday also, very interesting news. The capsule from the Hayabusa 2 mission successfully landed in Australia, bringing with her some material from the asteroid Ryugu, which will be the first sample from an asteroid that will be studied here on Earth. So that's quite exciting. For other news and events in December, our amazing social media team made a very cool calendar that you can see on Facebook, Twitter, and Instagram, containing all the fascinating space-related events, such as a total solar eclipse, 2 meteor showers, or the conjunction of Jupiter and Saturn. They come very close, it looks like. So don't forget to check our social media to stay updated on that. Next is our first speaker, Dennis Bodewits, who did his master and Ph.D. in astrophysics here in Groningen, and he is now an associate professor at the Auburn University in Alabama, in the United States. And tonight he will talk about alien comets in our solar system. Dennis, the floor is yours.
Okay, let me start my screen share. So first of all, Hayabusa 2 is the second mission to bring back an asteroid sample. Hayabusa 1 was the first one. Hayabusa 2 is different in that it brings back material from a different kind of asteroid, a primitive one, which may or may not be related to comets and which may or may not have volatiles. So I'm going to talk about comets from other solar systems that are flying through our own solar system, so alien comets in our solar system. And as I was introduced, I am a professor at Auburn University. So where is Auburn University? I marked it here for you on the map. So you have Atlanta here. This drive is about an hour and a half, and that takes you to our town. The university is a little smaller than Groningen University, but not by much. We have about 27,000 students versus 30,000 in Groningen. And we're also about 3 hours away from the nice beaches here on the Gulf of Mexico. So why does a Dutch person choose Auburn University? Well, I show you the image on the right, and you can guess which one is a Dutch soccer game and which one is a Auburn football game. You see they're very similar, but there are little hints there. There are little Dutch flags everywhere. So the top one is the Netherlands. The bottom one is Auburn University. Also, the people are wearing less clothes in the Auburn photo because the weather here is a little bit nicer than it is in Groningen. So what it is that I do, I study, I do astronomy in the lab mostly, so laboratory astrophysics. So what is laboratory astrophysics? Anytime you have a new space instrument or you do measurements remotely, you will have to first understand the atoms and molecules that you're looking at. So what we do is make sure that we can actually interpret the astronomical data. And the main goal of our field is to make sure that atomic and molecular data is never the bottleneck in the interpretation of astronomical data. So what are comets and asteroids? So you see here a cartoon from the New York Times, which is called Name That Space Rock. And essentially what you have here is a comet. A comet is a small body with a lot of ice and rock in it. An asteroid has much less ice, maybe no ice, and smaller fragments of it, like a meteoroid, is just a grain which burns up in the atmosphere, becomes a meteor, and when you find it on the ground, it's a meteorite. The reason why we're so interested in comets and asteroids is that they are the leftover Lego blocks from when our solar system was assembled. And comets in particular are the ones that contain volatiles. So you can say something about where water and complex molecules come from. In reality, the picture is a little bit more complicated. Often we only recognize comets because they have a tail when material from their interior sublimates. But there's also asteroids that sometimes have tails. So there is a gray zone between comets and asteroids. When the planets were formed initially, a couple billion years ago, the solar system was a different place. Comets formed relatively close to the sun, but far enough away that you can have water ice. And then at some point, the giant planets, Uranus and Neptune, they changed positions. And of course, that caused havoc in the solar system, and the comets were ejected outwards. And so nowadays, the comets are stored in two reservoirs. We call them cold storage because they're very far away from the sun. The first one is the Kuiper Belt. Pluto is part of the Kuiper Belt, and it's around 100 AU from the sun, where an AU is the average distance between the Earth and the sun, or 150 million kilometers. The Oort cloud, which is about 1/3 away to the next star, is much further away. You can see it's about 100,000 AU from the sun. And that is a more spherical distribution where comets are stored even colder. Oort was, of course, named after Jan Oort, who is a Groningen alumni, if I'm not mistaken. So comets are so interesting because they contain a very large number of molecules. This cartoon here was made by the Rosetta mission, who orbited comet 67P, Churyumov-Gerasimenko, for 2 years, and it had a large suite of instruments on board, including a mass spectrometer. So this mass spectrometer found over 50 or 60 molecules of increasing complexity. For example, they found, shown here as a lion, they found an amino acid glycine, which is certainly it's the simplest amino acid, but it is clearly a building block of life. There were also many organic compounds, also everywhere here, like aromatic rings. There were some volatiles that were unexpected. So even though comets are relatively simple objects, the chemistry is clearly complicated. And of course, since this is astronomy on tap, I want to point out that there's also 5 different alcohols, although I suggest that you don't try them all. So Comet Borisov is the second alien object detected in our inner solar system. And alien, of course, is the fancy word for saying that it comes from out of our solar system. How do we know that? Well, the only reason that we can tell that is that its orbit puts it such that it cannot originate from the Oort cloud. Or in more physical terms, the comet's orbit has an eccentricity which is larger than 1. Now, this by itself is not the first time, but in all other cases, we could trace this back to the interaction of a comet with Jupiter that slightly altered its orbit and then resulted in this large eccentricity. For Comet Borisov, and also for the first interstellar object that was discovered in our solar system, Oumuamua, we can clearly tell that they've come from outside the solar system. Comet Borisov was very different than Oumuamua. Oumuamua was more asteroid-like. It was very small. We only had a very small viewing window because it was moving so fast, and it was also very faint. Borisov, on the other hand, was very active. It looked more like a normal comet, and it was observable for a month at a brightness of about 18 magnitudes. So if you're an astronomer, that means it means it's not really bright, but it could be picked up by smaller telescopes. So we organized a campaign to really find out what this object was made of. So I see that my sharing has stopped, so let me reactivate it again. Give me 1 second. Yeah, we're back. We organized an observing campaign to find out what this interstellar object was made of. And so the first telescope that we used was the Swift Space Telescope, which is a small telescope the size of a mini, and we used it to do ultraviolet observations. This campaign was led by my grad student, Lucy, shown here. This was the transit of Mercury, which is probably somewhere on this picture, but you can't quite see it. Swift can observe in the ultraviolet. And one trick that you can do there is to actually study the fragments of water. It is very hard to see water outside of our atmosphere because we have so much water in the atmosphere. This blocks our view outwards. But this water, when you expose it to sunlight, it falls apart in OH, hydroxyl, and H, and that emits very brightly in the UV. And so these 4 images here, you can see that the comet is very faint. It's merely a blob. But this actually are images of a cloud of OH surrounding that interstellar comet. And here you have a V-band image. So this is optical light, and you can see its dusty tail there. And so what we observed this comet over a period of a couple of months, and we found that it was producing water by as much as 30 kilograms per second. And that number is important because it allows us to estimate how much material was removed from the nucleus. The nucleus is thought to be very small, about half a kilometer in radius. And so in that case, it lost anywhere between 0.2 and 1 meter of material off its surface. So if you consider it an onion, there's a significant amount of material that was removed from the surface, more than where sunlight can penetrate in the comet's nucleus. The second campaign was with Swift's bigger brother, the Hubble Space Telescope. And what we did there was ultraviolet observations with a technique called spectroscopy. And an example of what we saw is this here. So this is the fingerprint of carbon monoxide molecules in the ultraviolet. We were surprised, given that how faint this comet was, how bright this signal was, and it really meant that this comet was producing a lot of carbon monoxide. And how much that is, let me illustrate you that here in this graph. So this graph, we have on the x-axis, we have time. Perihelion is the point closest to the sun that the comet came, and that was about 2 AU at December 17. So on the left of that, you have time before perihelion. On the right of that, you have the time after perihelion. So in blue, I show you here the water production rate, and it's in a funny unit. It's in units of molecules per second. And as I said, this peak here corresponds to about 30 kilograms per second. So you see that as the comet was getting closer to the sun, it was getting hotter, more water ice was sublimating, and then until it reached a maximum here at perihelion, at which it dropped really quickly. We don't know why it dropped off so quickly, but at the same time, when you look at the black dots, these indicate the production rate of carbon monoxide, and that the arrow bars are significant because this was very hard. But you see that it stays about constant in this 1 month of observations. Now, 2 points to remark. So the first thing is the amount of CO. We've never seen as much CO produced by a comet as we've seen for Borisov. Regular comets, they have about 0.2 to 23% of CO with respect to water. Typical values are 4%. Borisov, when you look here, there may be, in our measurement, about 150% CO with respect to water. So much more CO than water. And second, why does this curve look like it does? So what we think that happens, as I explained about the Swift observations, is that this comet was so active that it lost a really large amount of material. We peeled away maybe a meter of its surface. Comets do not conduct heat very well, very poor heat conductors, so heat only gets a few centimeters at most below the surface. So that means that when we peeled away this 1 meter of material, we probably exposed much more primitive material that had not been heated before. And this is why it's so interesting to see that this CO is so active, because carbon monoxide has a sublimation temperature of 25 Kelvin or minus 200 degrees Celsius, as opposed to water, which sublimates at much higher temperatures, 0 degrees Celsius by definition. So that means that you look at something that has been stored at really cool temperatures for a really long time, and that probably now you're also looking at material that hasn't been heated before. And that allows us to tell something about where comet Borisov came from. So we can't tell from its orbit. You can only tell a couple of million years back, and it had a distant interaction with a star there. And anything what happened before that dynamically, nobody knows. What we do know is that you can do some reasoning about it. So the fact that Borisov has much more carbon monoxide than our own comets means that it probably came from a place that had less solar radiation, less heat, but still had enough carbon monoxide close to the star so that it could form comets. The problem is, in our solar system, when it formed, sure enough, when you go far enough away from the comet, you'll have conditions where you can have ICCO. However, the local density there was probably too low to build any snowmen from. So as we'd like to say, Comet Borisov is an alien comet from a dark and cold place. There's an alternate theory. You may recognize this image. This is Arrokoth, a Kuiper Belt object, as imaged by the New Horizons mission. A team that used ALMA also observed carbon monoxide in 2I Borisov, and they suggested that maybe this comet is a piece of an object like this, a smaller fragment. We can't tell, but we hope that in the years to come, we'll be discovering many more of those objects. So what is changing, and you may know that, is that the Vera Rubin Observatory, or also known as LSST, is going to come online soon. And this is an all-sky survey that monitors the sky with a 10-meter telescope every day. And we're expecting to find much more faint and small objects with that. This is what I had about Borisov. I'd like to end with some pictures of my team, my postdocs, Steve and Kumar, Lucy, who you met, and she led the SWIFT observing campaign, grad students Thomas and Sean, and the undergraduates Johannes and Lauren. Thank you very much. You can find my website here, and I'm ready to take any questions that you may have.
Hello, Denis. Thank you for this very interesting talk on Borisov. I didn't actually know this comet, so I learned a lot. So we have a couple of questions. The first one being, how many interstellar objects per year do we expect to pass through the solar system, like Borisov?
Yeah, that's great. So of course, there also is a caveat, right? There's small number of statistics. We've only discovered 2 of them thus far. But with LSST, current estimates are at least 1 a year.
1 a year, okay. We are actively looking for them?
Yeah, so how this works is that these all-sky telescopes, they are especially intended for transient science, things that change. And of course, comets and asteroids, they move much faster than background stars. So you can very easily detect them in subsequent images. Also, if you look at discoveries over time, of course, these comets have been getting fainter and fainter. And now every comet that is brighter than 18 magnitude will be discovered. And that's already incredibly faint. And the Vera Rubin Observatory, with a 10-meter telescope, it can go even fainter.
Okay.
Yeah, so it's fascinating to me that this was discovered by an amateur observer, Mr. Borisov from, I believe, the Ukraine. And still, even though everything is roboticized and we monitor the sky so actively, there is still amateur observers who beat all the professionals with their big equipment to it.
So that means that can still happen. We can have more amateurs discovering comets. That's very cool. So that's a lesson for everybody listening.
Make sure you know your sky.
Some hope, yeah. So do we know from the trajectory which star Borisov encountered, or do we only know that it happened? Because you mentioned that it encountered the star.
Yeah. So working these things backwards is extremely uncertain. There's already an uncertainty in its current orbit, and of course, when you work that backwards, that uncertainty becomes even larger. So most people consider this very speculative. There was nothing in the near past, but a couple million years ago, it may have flown several thousands AU away of a star, but that was enough to change its orbit just a little bit to erase all the information from what was there.
Okay, yeah. So that's how we know. Okay. Okay, fun question. What is the chance that an asteroid comet hits the Earth and kills us?
So this is a question that I like to do in my astrobiology classes. So
okay.
which one is worse, an asteroid or a comet? And so there are multiple ways to think about it. So comets are much faster. So they have much higher impact velocity. 20 to 30 kilometers per second is quite common. The problem with comets also is that you won't know it up to about 2 years ahead of time. So not much that you can do. And also it would be much harder to change their orbit. However, there are fewer comets than asteroids. And also comets are very porous and have a low density. So the mass would be lower.
Yeah. Okay.
More asteroids, they're rocky. There's a whole size distribution going from anywhere from the small grains that I showed to things like Ceres. The chance that there's a couple of kilometer asteroid will hit us is not insignificant. Actually, close to where I live here in Auburn, there's an impact crater. It's in a small town called Wetumpka. And this was I think, a couple of 100-meter sized asteroid that must have hit here about 100 million years ago.
Oh, yeah.
It's really cool. I take my students in my astrobiology class there to see it.
Yes.
Once you know that it's there.
It's really cool in theory. I hope it doesn't happen.
It was a bad day for whatever dinosaur was walking around here.
Yeah. We have a last question. Why is a theory that Borisov was a part of the bigger comet is excluding the first theory that it's alien cold comet?
They're not necessarily excluding each other. It's just that how you think that comets form, and can you form comets under these conditions, or could you not come up with a scenario that it is that cold? It is also a question of how processed do you think that this object is. Yeah, it's neat. This other study was published by my former office mate from NASA Goddard, and they were published back to back in Nature Astronomy. So I think it's really neat to have just different ideas of how you can get these objects, how you remove them from your planetary system, and what you can or cannot tell based on the limited information that you have.
Okay. Oh, I see we have a question on YouTube. Are there any other significant differences between interstellar comets which are surprising with respect to the solar system comets?
Yeah, I love that question. So interstellar comets have long been like the holy grail of our field. I showed you the Oort cloud, and extends a third to about halfway to the next star. So you can imagine that star, if it has an Oort cloud, it also extends in our way. And some theories have said that half of our comets actually should be interstellar objects. However, we never knew what to look for. Is there a chemical difference? Is there isotopic differences? Do they behave different altogether? And so the only reason that we know that Borisov and Oumuamua were interstellar was because of their orbits. And so Borisov then was bright enough that we could first learn about its composition. And what we found was that everything was the same about this object as with our own comets. If we didn't know that it was interstellar, there was no way to tell it. The first gases that were discovered, well, it had a tail. The dust had about the same color as that of our comets. The first molecule to be discovered was cyanogen. The next one to be discovered was atomic oxygen, which is probably related to water. And the story became actually sort of disappointing. It's like, man, this thing, it's exactly the same.
Yeah, okay.
So we were happy to see that actually something was different with that CO. But of course, in the future, hopefully, now we know what to look for. Maybe we'll get one that is bright enough that we can really look into details like the isotopic signature and those properties.
Okay, that's a good possibility. Yeah. Okay, thank you for your talk and for answering all these questions. And I guess we will see you at the Zoom pub later on.
Absolutely. Thanks, everybody.
So our next speaker is Yamila Miguel, and she's an assistant professor at Leiden Observatory and SRON here in Groningen. Tonight, she will tell us about Jupiter in the history of our solar system. So quite exciting. Yamila, you can start.
All right. So hello, everyone. I'm just having a little crisis here because my cat decided to walk on my keyboard, and now I cannot find the Zoom screen anymore. Just give me like 5 minutes, and I'll try to be back on track. Yes, here I am. Okay, sorry for that, guys. I hope that you can see me. Can you?
Yes.
Okay, great. Thank you. Okay, so let me share my screen. All right. So hello, good night, everyone there. I have my beer here, really prepared for this Astronomy on Tap. So I'm Yamila Miguel. I'm an assistant professor at Leiden, so close by. I'm not so far away as the first speaker. And today I will be talking about the work that I'm doing, working with Jupiter interior particularly. And I will tell you a little few things about the Juno mission, that is the mission that is orbiting Jupiter right now. So to start, let me just put everyone on the same page. So Jupiter is a giant planet. It's the biggest giant that we have in the solar system, and it's the biggest planet that we have in the solar system. So in this nice figure here, we can see the sun, that is the biggest object in the solar system, our shiny star. And then we have the planets. As you can see, Jupiter is by far the biggest planet in the solar system, followed closely by Saturn, and then we have the ice giants, Uranus and Neptune, and finally the small rocky planets, the Earth right here, Venus, that is our twin, and then we have the tiny Mars and Mercury. So Jupiter is by far the biggest one. That's why we call it the giant, gas giant. And they are both, Jupiter and Saturn, are very important planets to understand really the origins of our solar system. So when the solar system was formed, like long time ago, at the beginning, first the sun was born, and then from the remainings of the formation of the sun, there was a disk created around our sun. And this disk had dust particles, but also gas. And from this disk, all the solar system was born. All the planets were born. But the first planets that are formed in our planetary system are the giant planets, Jupiter and Saturn. Those are the first planets that were born in our solar system. They were born in the first few millions of years, which is very, very tiny time scales when we are thinking in astronomical terms. And all the other planets, we believe that took much longer time to form. But of course, the formation of the entire solar system is not something that we completely understand. There are many things that we have to learn, but we do know that the gas giants were the first ones to form. And for that reason, they have very valuable information in their interiors and their atmospheres to understand the formation of our solar system, to understand those first millions of years of the formation of our solar system. So that's really why we want to know more about these planets. We want to know more about what they are made of, about their interiors, about their atmospheres, because they are really a key in this puzzle that is understanding the evolution and formation of our solar system. Now, Jupiter is, as I told you, the biggest planet that we have, and it's also the closest giant to the Earth. It's not so far away. So we went there many times and took information. So this is kind of the history, our history, observing Jupiter. And of course, this history started many years ago with Galileo and his telescope. But since then, we can observe Jupiter here with even binoculars, with the naked eye. It's just very, very bright in the sky. But we also went there with many missions. And the first missions that actually stopped by Jupiter were the Pioneer missions, the 10 and 11. Then we had the Voyagers, 1 and 2. And after that, we had the Galileo probe that was in the 90s. And that was a very good mission for Jupiter because it orbited around the planet. It also entered into the atmosphere and took some in situ measurements. So it was a very, very good mission. After that, we had Cassini that actually went to Saturn, but on the way to Saturn also did a flyby around Jupiter. And then we had New Horizons that also Jupiter was not the final destination. It went even to Pluto. But on the way there, it also did a flyby and took some images, some information on Jupiter. Finally, we have Juno, that is this one here. Juno is a NASA mission. It's been orbiting around Jupiter since 2016, and it's really been giving us amazing information to understand this planet much better. The image that is on my background is one of the images that Juno took. So I'm going to tell you a little bit more about this, but first of all, I want to tell you which are the things that we would like to know about Jupiter. Because of course, Jupiter is, as I said, very close by. We went there many times. So then the question is, well, which things would you like to know? And the truth is that there are many things that we still don't know about Jupiter. I'm particularly interested in studying the interior of the planet and the deep atmosphere. But there are many, many questions that we still don't know. And they are very fundamental questions to understand the formation of our solar system. So today I have 15 minutes. So I'm going to tell you about only one of all those questions that we have, but I'm happy to discuss more about Jupiter later on. And really the question that I would like to answer to you today, and that was something that I was doing research on the last years, is understanding a little bit more about those bands that we observe in Jupiter. So when we see Jupiter, even with a small telescope, we see this characteristic band pattern that, of course, I put here Galileo because we've been observing this band pattern since a long, long time ago. And here you can see it very nicely in this movie made by Cassini. And you have here all the famous bands of Jupiter. You see that they rotate in different directions at different velocities. So one question that we always had, and this is really a problem that we have in astronomy, is that we are seeing in 2 dimensions, right? The third dimension is always a problem to us. In this case, it's the same thing. We wanted to know which is the depth of those winds that we are observing. Are they like going all the way to the center of the planet, or do they stop at some point? Jupiter is not really a planet like the Earth. Jupiter is a gaseous planet, which means that there is no surface where we can go and step on. Jupiter is more similar to the sun than to the Earth. Let's put it like that way. So then, of course, we have these bands, and we were like, well, when do they stop? Do they go all the way to the center or not? And this is very important for us because we need to understand the depth of these winds in order to understand better the internal structure of the planet. So this is really the key question that I want to discuss with you more today, which is the depth of these bands that we see in Jupiter. And this has been, as I mentioned before, a question that we had for many, many, many years. And will tell us also something about how the planet rotates, how it moves. Because as you can see here, it's not that if we count the movement of the great red spot around Jupiter will tell us how is the rotation, how is the 1 day around Jupiter. It's not like that, because all these bands rotate at different velocities. So this really is a study to understand how the planet moves, and that also helps us to understand its interior. So to understand this a little bit better is why we sent the Juno mission out there, actually. We wanted to understand more about the interior of the planet, about the atmosphere, about these bands that we observe, and this will help us to understand the origin, the formation of Jupiter and our solar system. Now, I'm part of the Juno mission, and I will tell you a few more things about it. So here, what you can see in this nice video is all the Juno team. Here you see we got together 1 day before, actually we got together the entire week, but this image was taken 1 day before the mission arrived to Jupiter. And here you can see the spacecraft, well, of course, not a real one, but an image of how it would be in real size. And in all this side, we have the scientists working on the mission, and on this side is the engineers. I'm like right there, standing. And it was really a party for all of us when the mission arrived to Jupiter. The space is very difficult. It's not so easy to actually reach a planet the day that you want this mission to reach, with all the problems that might be the launching, the going there, the calculations, that on the instruments work. So it was really a party. We actually had a huge party. where we make these kind of like fake tattoos. We were all got together with the press, with our families. We got all together in one room, trying to hear at the moment when the mission was arriving. And here is all of us celebrating when actually we got results saying that everything was okay and the mission was in good health. So it was really amazing, an amazing experience to be part of this mission and to be working with this data since it arrived to Jupiter in 2016. Now, Juno has been orbiting around Jupiter, as I mentioned, since 2016. And the orbit that it has is kind of like that. It's very elliptic. It takes around 2 months for the spacecraft to go around the planet. And at the beginning, it was going to have a different orbit, actually. The planning was that it was going to have an orbit of around 2 weeks. But then when we put it in this initial orbit, there were some problems, some issues, and then we decided to stay safe and stick with this initial orbit of 2 months. So this is the orbit that Juno has right now. And on this other side is kind of an animation of how Jupiter will look like if we look at it from the spacecraft. So I think it's a cool animation to show to you. Now, let me show you a few more things about the spacecraft. And here you can see its size compared to one person that is here. And it works with solar panels. It's actually the first NASA mission that goes so far away and works with solar panels, which was also a lot of engineering to work the orbit. So then it will be always looking at the sun to get the energy. Also, it's not only doing the gravity data, that is really the data that I'm using to work with the interior and with the deep atmosphere, but it's also doing other measurements about the magnetic field, the atmosphere of Jupiter, and now we are, hopefully, we will get an extended mission to work a little bit more on the moons as well. But besides all those nice instrumentation, it has other surprises inside. It has some passengers that I found very cute, that are these Lego figures. So the original idea was actually to have a bone of Galileo inside the probe. That was the idea of the PI and the team, but of course the Italian government didn't want to know anything about this. So then in replacement of Galileo's bone, they put these nice Lego figures, which represent this one here. He's Galileo holding his telescope. And then we have here Jupiter, the mythology figure. And here is Juno, that was actually in the mythology the wife of Jupiter, that could see through the clouds to see what was Jupiter doing. So that is the whole idea of the mission, that it was going to see through Jupiter clouds to understand all the mysteries that lay inside the planet. Now, it has this nice instrumentation, it has these passengers, and the mission also has a camera. And these are some of the most beautiful images that we have from Jupiter today, taken by the JunoCam. So this is a time lapse that was like, we got all different images and put them together in a movie. And this is a real Jupiter in the moment where the spacecraft is passing closest to the planet. So if you remember, we had this very elliptic orbit. At some point, it's passing very close to the planet and it's taking these amazing images. So this is, before you ask me, this is real Jupiter. These images are not colored. They are, you can go to the website, download the raw images and play around with the colors, with the contrast, and make things like these ones. So this is real Jupiter. The contrast and the color might be enhanced a little bit, but this is really how Jupiter looks like, which I think is truly amazing. We've never had images with these details before. Now I have a few other images to show you. These are really just my favorites. As I said, you can go to the website and check them by yourself. This one is really like, it seems like it's painted, but it's true Jupiter. This one also is beautiful. This other one where we can see also these bands that I was telling you at the beginning. Here is much closer, and you can see all the turbulence that Jupiter has in its atmosphere. And this one, I think, is one of my favorites, is the North Pole. And you can really see all the turbulence and the bands really appearing up here. This is truly amazing that we have images like that. Now, just to finalize, let me tell you one more thing about the data that we get. And the thing is that if Jupiter were perfect, a perfectly symmetric planet, perfectly homogeneous, all the matter distributed homogeneously, then we would have that the spacecraft would have an orbit that looks like this blue line here. Now, in reality, when we communicate with the spacecraft, oops, sorry, I went too fast. In reality, when we communicate with the spacecraft, we get an orbit that is a little bit different from that perfect blue orbit. And it's more like the orange one that you are going to see appearing here. So this is the perfect orbit that we can calculate doing math. And this orange one is the true orbit of the spacecraft. So the differences between the two are because Jupiter is not perfect. It's not a perfect sphere. It's because the matter is distributed differently in different places. And that is giving us information on the gravity field of the planet. Those little inhomogeneities really tell us, map a little bit the gravity field of Jupiter. So we use that data to study the interior, to study the atmosphere, and to study the depth of the winds that I showed you before. So using this data, we could understand a little bit more about these bands for actually the first time ever. And it is shown in this nice movie that NASA made for the press release of our papers on this, where we discovered that these bands extend around 3,000 kilometers into the planet. That is more or less 4% of the radius of Jupiter, which is not a lot, really. It's kind of little. And what happens beneath the clouds is that the planet rotates as a rigid body. It's not a rigid body, it's a fluid. Remember that I told you before, it's like a gas and actually some liquid, metallic liquid has inside. So it's not a rigid body, but it rotates as if it were a rigid body. And then we have the bands that rotate more differentially that we can see on the outside. Okay, folks, this is all I wanted to tell you today. I'm really happy to be here. And of course, I would love to answer any other questions that you had about Jupiter. And I leave you here with all the team that was working with me so far in this beautiful mission. Thanks.
Yep. Thank you, Yamila. Very, very, very impressive pictures of Jupiter. I have never seen them myself. I didn't know we had such. I mean, one of the questions I had was, is it even real?
Yeah, they are amazing. They are real. I tell you, you can go to the website and download the raw images yourself.
Yeah, and we have that since what, 2016?
2016.
Wow.
Yeah.
That is really something. So yes, we have a couple of questions. So first from YouTube is, are the Jupiter bands similar to the Hadley cells on Earth or an entirely different mechanism?
It has some similar mechanisms in some parts, but
can you explain just quickly, maybe for everybody, the Hadley cells on?
So you have a circulation in the atmosphere of the Earth that it has to do also with some places being hotter than others and how you transfer all that energy in the atmosphere.
Okay.
So the atmosphere of Jupiter is kind of similar in many ways. We actually use similar models that we use for the Earth as well. It's different in others, though, because it doesn't have a surface, for example. So it doesn't have the friction or the heating or anything that comes with surface interaction between the surface and the atmosphere, because Jupiter doesn't have a surface.
Yes.
But also because it's farther away from the sun, the energy that it receives is much, much less than the one that the Earth receives.
Yeah, that makes sense.
So that also changes a little bit the circulation of the atmosphere. But in a sense, the models that we use are similar to the ones that we can use on Earth.
Oh, okay. Okay. That's okay. How do we know that Jupiter and Saturn were formed first in our solar system? You explained at the beginning that they were the first planets.
Yes. So the thing is that they have what we call a primordial atmosphere, meaning that all this gas that these planets are made of was gas accreted directly from that disk at the first moments of the solar system formation. The gas that we have on Earth's atmosphere, for example, was not accreted at that moment. It's not a primary, but a secondary atmosphere, meaning that it was formed during the evolution of the Earth from gases that were cooling down and were coming out from the magma or from impacts or other effects. So we know that in order to form these planets, as big as they are, they needed to be formed at the moment when there was still gas in that disk. And the gas in the disk, in the primordial disk, evaporates very quickly. So then they needed to form in those first millions of years.
So it comes from their size. So being this size, we assume that they have this gas, and having this gas means that it was only at the beginning.
Yeah, exactly.
Why do the atmospheric bands move in opposite directions?
So the bands that we see are an effect of the rotation of the planet. So the planet rotates very quickly. Jupiter has one rotation in less than 10 hours. And imagine, Jupiter is really gigantic and it rotates much faster than the Earth. So then that intense rotation really shapes all the fluid that you have around it. And that's why we have these bands. And that's also why they have different velocities, different directions. It's just a result of the crazy, how the fluid behaves when it has this rotation.
It's because Jupiter rotates fast that we have...
It's the Coriolis force.
Okay.
Yeah.
To become gas giants, do planets have to be far from the star, or can you have a giant planet close to the star?
Oh, that's a great question. So if you asked me this same question 30 years ago, I would have told you giant planets are only far away. Yeah. That's the only thing we have.
Because we didn't have it before.
Exactly. Now we discover the first exoplanets, and many exoplanets that we are finding are giant planets like Jupiter, but they are very close to the stars, much closer than Mercury to the sun. So we know that giant planets exist also very close to their stars. And we are trying to understand why those planets are there and why the ones we have here are so far away. That is not an answer that we still have.
No, but that's an interesting field for sure.
Yes.
How deep is the Great Red Spot?
How big?
Yeah, how deep?
Oh, how deep? Okay.
Depth, right? So
yes.
It's the same depth as the bands?
So it's not the same depth of the bands. It's smaller. We are about to, there is a paper coming out very soon about that, and I cannot tell you much more about it, but it's much less than the depth of the bands.
Okay. Yes. Okay, that's okay. So we have a couple more questions, but I think we will stop here, and I hope these people will join us to ask during the Zoom pub. We just have one last question that we'd like to ask is, what is your cat's name?
My cat is Sirius White, and I'm very sorry that he screwed up my first minutes of the talk.
Yes, we can forgive. And we hope to see him during the Zoom pub.
Yeah, he ran out scared because I was like, what did you do? But he might come back.
Yes, perfect. Okay, then we will see you. You can also participate to the pub quiz, of course. And yeah, we will see you later during the Zoom pub.
Great.
Okay. Now for everyone, we are gonna move to the pub quiz, and unlike other editions, we don't have the pub quiz on YouTube anymore. You have to go on Zoom. That will be displayed on YouTube. And I hope you will join us and try to win our amazing prize.
So please join us in the Zoom pub. Follow the link. The YouTube stream is going to end soon, and we will just be in the pub. So please come join us there if you would like to, following that link, // stem.000/ZoomPub. That will then launch Zoom on whatever device you're using, so you can join the quiz. I'll leave the link there for about 1 more minute. If you get into the ZoomPub, they will share the Kahoot pin number for the quiz right now also in